Welcome to Brain Vision.
Hello and welcome. The first part of our question asks us to find the reduced mass of a hydrogen-like atom consisting of a proton and a muon. The reduced mass, which I will denote as m sub r, is equal to the product of the two masses over the sum of the masses. Now we've been given that the mass of the muon is 207 times that of an electron. And so we can rewrite this as follows. Where 207 ME is the mass of our muon. We then plug in the values of the mass of a proton and that of an electron. If you do this carefully with your calculator, you will arrive at the reduced mass as 1.69 times 10 to the power negative 28 kilograms. And that brings us to the end of part A. For B, we are to find the ground level energy in electron volts. And I'm sure you'll recall this hideous looking formula for the energy of the nth level, giving us this. The m sub r in this formula is the reduced mass of the atom, the hydrogen-like atom. In the case of the hydrogen atom itself, the mass of the electron is usually put in place of the reduced mass, and we shall soon see why this is so. Now, if you look at this formula carefully, it seems to bear some semblance to the formula that gives the ground state energy of a hydrogen atom. In order to make that more clear, I will be multiplying both sides by the reduced mass of the hydrogen atom. And then it is now easier to see that this quantity here is simply the ground state energy of the hydrogen atom, which is equal to negative 13.606 electron volts. And so we can now write down our energy in a simpler way as m sub r over m sub h multiplied by negative 13.606 electron volts over n squared. Luckily for us, we found the reduced mass of the hydrogen-like atom. But how about the reduced mass of the hydrogen atom? Find that, and you can try this by using the same formula from that make up the hydrogen atom. So if you do that carefully, you would realize that the reduced mass of the hydrogen atom is equal to 9.104 times 10 to the power negative 31 kilograms. Now notice how this value is similar or very close to the mass of the electron. And this explains why sometimes we may use the mass of the electron in place of the reduced mass of the hydrogen atom. So you may ask, in that same vein, why can't we just use the mass of the muon as the reduced mass? Why do we go through all this trouble of calculation? Now the truth is, the approximation of using the mass of the smaller particle as the reduced mass of the system, that approximation is only good if the difference in mass between the two particles is so large. So, for instance, taking the hydrogen atom, the proton is several times more massive than the electron, more than 1,000 times, and so that approximation works. But taking the muon, the proton is only about 10 times larger, more massive than the muon, and so that approximation will not work quite well. And so we might just as well calculate the actual reduced mass and use it in our calculations. Now that we have the reduced mass of the hydrogen-like atom and that of hydrogen, and for the ground state we know N is equal to 1, we can plug in those values and find our energy. If you do that carefully, you will find out that the energy is negative 2.53 kilo electron volts. And that does it for B. We now come to C, where we are to find the wavelength of the transition from n equals 2 to n equals 1. And we are going to resort to the idea that the change in energy during the transition is equal to hc over lambda, where lambda is our wavelength in meters. Fortunately for us, we have found a simpler way of writing down the energy, En. And so we can write down the change in energy between the two levels in terms of this expression, noting that for the final level, n is 1, and for the initial level, n is 2. So our expression for the is as follows. Sorry. Equals hc over lambda. Because we need our answer in meters, it is imperative for us to convert this energy from electron volts to standard form in joules. And you'll recall that 1 electron volt is equivalent to this in joules. And so we have our m sub r and our m sub h. We can convert this into joules by multiplying the value here by this. And so if you do that carefully, you will arrive at this value in joules being equal to hc over lambda. It then becomes easy to make lambda the subject. Lambda equals hc over that, which gives us six point 55 times 10 to the power negative 10 meters. Can you rewrite this in nanometers? I am sure you can. This is going to be 0.655 nanometers. This brings us to the end of our solution. Thank you for watching.